Thank you very much, Steve, and thanks to the organizers for inviting me and IPAM for hosting the event. So my talk will not be directly related to machine learning, but I'll talk about an important tool that you use in machine learning, and that's optimization. If you do everything else right and your optimization does not converge to a suitable minimum, gets stuck in local minima or saddle points, then the results you get are not very reliable. So it's really important to use good optimization algorithms. The setup of the problem that I will talk about is pretty simple. It's the following. You have an objective function f that you would like to minimize over a set of parameters. Let's denote them with x or variables x. Usually the function f is from Rn to R, or a subset of Rn, denoted here by the curly x. And I'll assume that you have a global optimizer or minimizer, more particularly, that lives in the set x. Ideally, you would like to stop here and don't say much more about the function f, but unless you make other assumptions, any mathematical work on these equations would be futile. So what I'll do is I'll also make routine assumptions that people make in convex optimization. I'll assume that the set x is convex. The function f itself is convex also. And because I'll talk about gradient-based methods, I'll also assume that the function is at least once continuously differentiable. I will not assume that the function is strongly convex, but later on one of the slides, I will talk about or comment on the strong convexity. So I thought I'd just put the definition to refresh your memory. A strongly convex function satisfies this inequality for any 2 points x and y. For convex function, this is correct with m equals 0, but strong convexity requires slightly more, that there's a positive constant m for which this inequality holds. Let's do an overview of the methods that I will consider today and comment on their properties a little bit. Well, the most familiar method for optimization, perhaps, is the gradient descent. You start with some initial point, and then you update the point by moving in the opposite direction of the gradient of the function. And it's also known that its convergence rate is 1 over k, which means that the difference between the value of the function at the point xk and the minimizer x star is bounded from above by a constant times 1 over k. So as iterations go forward, the difference goes to 0. Another method that I will talk about is the Poyax heavy ball descent, which is quite similar to the gradient descent if you look at this part, except that for the first xk in the gradient descent, you have another point yk. And yk is given as a linear combination of the current iteration xk and the previous iteration. So it also depends on the previous, where you were previously. Its convergence is also 1 over k. However, that constant that comes in front of 1 over k is much smaller than the one in gradient descent, so it really converges much faster, typically in applications. The last set of equations that I will discuss is the Nesterov accelerated gradient descent, which was developed almost 20 years after Poyax heavy ball descent, and finally brought the optimization algorithms from convergence rate 1 over k to 1 over k squared, which is much faster than the previous methods. On the face of it, it kind of looks exactly like the Poyax heavy ball method. However, there are two important differences. One is that the constants lambda and s, the scalar constants, are not constants anymore. You have to update them based on the iteration as you go forward. And one other thing is that the gradient is not evaluated at xk, it's evaluated at the point yk, which has this relationship. And again, it depends on, yk depends on where you are now and where you were before in your iterations. Gradient descent is very intuitive. Well, you move in the opposite direction of the gradient and you expect the error to decrease. However, the other two methods kind of, if you just stare at them, look mysterious. Where did they come from? How did they come up with? It's less mysterious, actually, if you look at the continuous limit of these equations. Basically, what I'm trying to say is that the gradient descent, we all know that is a discretization in time. of the gradient flow, right? You discretize with step size s, and you get the gradient descent. In fact, Polyak, he derives his method in the 64 paper by starting from a second-order differential equation and then discretizing it to get his iterations. Notably, these are second-order differential equations, while the usual gradient descent is the first-order differential equation. So that the iterations really come from, again, discretization of the differential equation. Nesterov, however, acts in mysterious ways. If you look at his paper, he just writes down the iterations, and it tells you what lambda and s should be, and then he proves that they converge 1 over k squared. So nobody knows really how he came up with it. But it took more than 30 years for Sue, Boyd, and Candace from Stanford to realize that actually, in a proper limit, these iterations are also discretization of a second-order differential equation, and they wrote down the proper differential equation. Rho is a constant, which is 3. For rho equal 3, you get actually this discretization. One important fact about this equation is that unlike Polyak's differential equation, it has an explicit dependence on time t. So it's a non-autonomous second-order differential equation. There seems to be a singularity at t equals 0, but it's an integrable singularity, so it's not really important. You can integrate through it, and your solutions will look at least continuous. So the goal here, however, for this talk is going to be the following. I would like to study the phase space of these gradient descent methods in the continuous time, and try to analyze their phase space structure. Let me maybe tell you a little bit about the results before I show them in detail. Basically, what I will show you is that these two second-order differential equations have an invariant manifold in their phase space. This invariant manifold is attracting, so wherever you really start, you converge to this invariant manifold. I will give you expressions for estimating the shape of this invariant manifold, and to the first order of approximation, that invariant manifold is, the dynamics on the invariant manifold is just gradient descent. And then higher order approximations of that invariant manifold make the difference between the convergence of the gradient flow and the other two flows. So that would be the program. As I go ahead, feel free to jump in if you have questions. It would be fine. Before I start with the results, I would like to make a couple of comments about the accelerated gradient methods. When I refer from now on to accelerated gradient methods, I mean either Polyak's heavy ball method or Nesterov's accelerated gradient method. So if you look at those iterations, this is the gradient descent on a particular function. If you look at, I think this one corresponds to Nesterov, but it would be similar for the heavy ball method as well. You will see that the decrease in the error as opposed to the gradient descent, which is monotonic, is not monotonic anymore. There are oscillations. However, although there are sometimes the error increases and then decreases again, overall asymptotically the convergence is much faster still than the gradient method. The oscillations are not that surprising if you realize that it comes from a second order differential equation. Second order derivative allows for oscillations in time. The other thing I want to mention is the fact that it's a well-known fact that the gradient descent does a lot of zigzag motion. Maybe that figure doesn't do it justice, so I'll just draw it here. So if these are level sets of the function f that you want to minimize, so these are fx equal to some constant. If these level sets are very elongated in one direction, then the gradient on the horizontal axis here would almost be orthogonal to the horizontal axis, almost orthogonal. So gradient flow, the continuous one, will have no trouble. You just come down very quickly here, and then you converge to the minimizer, let's say, which is here. So this is x star. But as soon as you start discretizing this and doing the iterations of gradient descent, it is also well known that when you get close to the horizontal line, you do a discrete step, and you step over to the other side of the line, and then you do another step, because the gradient is almost orthogonal to to the horizontal line, you step on the other side, and a lot of these zigzag motion takes place with very little progress really towards the minimizer x star. However, if you look at the corresponding iterations for the heavy ball method, you see zigzags, but the zigzags are not as severe, and you converge faster to the minimizer. Well, this is well known, but I would argue that actually it's not a very good way of looking at it. A better way is to look at these in their appropriate phase spaces. These are second-order differential equations, so this phase space consists of x and x dot. X is in Rn, so the phase space is R2n. And what is really happening is that the trajectory of the accelerated gradient descent is inside that R2n space. So when it does these oscillations toward the minimum, it has the higher degrees of freedom, access to higher degrees of freedom. So it oscillates out of the x-plane and comes back. Of course, when you discretize it and project it onto the x-plane, you get something like this. However, I think the better way to look at it is to look at it in the actual phase space. For gradient descent, the phase space is really the gray plane itself. So it doesn't have access to those higher dimensions. One last comment about the accelerated methods is the paper by the group of Michael Jordan at Berkeley that showed that actually all of these gradient descent methods can be written as stationary curves of a Lagrangian function. The Lagrangian looks like this. Alpha t, gamma t, and beta t are functions of time to be determined. And when you pick them in the right way, you get various accelerated gradient methods. If you write down the Euler-Lagrange equation for this Lagrangian, then you get these sort of equations. I should also mention that this norm here is the Euclidean norm, but you can do more complicated norms as well, and they've done that. So you get the Euler-Lagrange equations, and you see already that if you pick alpha in a way that this always remains a constant, and this also remains a constant, you get the Poyax method. So this becomes a constant, that becomes a constant. And that choice of alpha and beta looks very restrictive, but actually for any mu and eta for which these logarithm functions exist and they're well defined, you can define those alpha and beta, and you get the Poyax method. If you pick alpha and beta in a slightly different way, you get Nesterov's method. In that paper, they do a lot of other things as well, but that's the big message of the paper that I wanted to convey. So with that, let me jump into what is new that I want to talk about today. What I want to say first is that the motivation for the multiscale analysis of these methods is the following: that if you look at Poyax method, for instance, it looks like a like a damped mechanical oscillator. The damping here being mu x dot, right? Often these damped systems have invariant manifolds in their phase space. People have studied this for a long time. So the question is whether these accelerated gradient methods also have such invariant manifolds. If they do, what is the shape of this manifold? And what is the dynamics reduced to these invariant manifolds? And I'll show you that actually this fits very well in the framework of geometric singular perturbation theory and gives answers to these questions. So let's focus for now on Poyax methods. As I said, Nesterov's method is a little bit more complicated because it's non-autonomous. I'll come back to it towards the end of the talk. But for now, let's just focus on this set of differential equations. One thing you immediately can do is to write it as a system of first-order differential equations. Rescale time, divide by mu, and then you get some parameter epsilon, which is 1 over mu. And rescale time to define the rescale time tau, which has this relation with the original time t. And the derivatives with respect to tau are here denoted by primes. When you do all that, you transform this system into this system of equations. Now you see that if you put epsilon equals 0, then x prime is 0, and v prime is just minus v. And here is the geometric picture that goes with that. This is a 2n-dimensional phase space. So this is the sketch of that 2n-dimensional phase space. This is a n-dimensional subspace, and v corresponds to another n-dimensional subspace. For epsilon equals 0, x does not change, so your fibers are basically straight lines. Anything that lives in v equals 0 plane subspace will be a fixed point of the system. So all these points in red are fixed points of the system for epsilon equals 0. For anything that is away from this critical manifold M naught, you have these fibers which are associated to this exact solution Vt equal V naught E2 minus tau. So you have exponential convergence to the critical manifold M naught for epsilon equals 0. That's trivial, but non-trivial things can happen once you increase epsilon to a positive parameter. And the question is whether this manifold deforms slightly into an order epsilon close manifold M epsilon, and whether we still have these fibers where we converge towards this slow manifold M epsilon. And if that is correct, what is the expression that estimates this manifold? This is the subject of basically this theorem that says, in fact, for mu large enough or epsilon small enough, actually that manifold does exist, that invariant manifold. It's still attracting, so everything converges to it exponentially fast. And also the expression for the manifold when it exists is given by this series expansion, where the functions g are defined recursively. The first function only depends on the gradient of f with the parameter eta in front of it. All the even order terms vanish, and the odd terms are, as I mentioned, are recursively defined in terms of the previous g's. One thing that I've highlighted is that it says that there exists a mu naught for which if mu is larger than that value, then you will have the existence of this slow manifold. Unfortunately, it's not easy to say in general what mu naught is exactly. It depends on the function f you have. And except for very simple cases of f, you cannot derive an expression for mu naught. But I'll show you when we go to the examples that actually that mu naught is not necessary to be very large. Even moderate small values of mu naught will work. The point being that usually the values that are used for mu in the heavy ball method are in the relevant, satisfy the relevant assumptions here. So as I mentioned, I have these expressions that basically, as I increase the order of accuracy, gives me better and better approximations of the slow manifold. And g's I can explicitly compute them. So let's look at some of these approximations. For the first order of approximation, where I only consider the epsilon to the 1 terms, it is basically the gradient flow. So your slow manifold, the dynamics on the slow manifold is simply gradient flow. You can always rescale time and get rid of epsilon eta for it to be the standard form of the gradient descent. So what happens, you very quickly converge to the slow manifold. On the slow manifold to the first order, you have this. So initially, you're very different from the gradient flow. But as you converge to the slow manifold, you get closer and closer to the usual gradient flow. The minimizer, the x star, which was the minimizer of f, is part of the slow manifold. And moreover, it is an asymptotically stable fixed point of the system. That is not hard to show. You just take a Lyapunov function like this and prove that the fixed point is asymptotically stable. The reason it's fixed point is obvious also because the gradient at the minimizer vanishes, so you get a fixed point. Now, if you go higher in the order of approximation, you get epsilon squared term, as I mentioned, vanishes because g 2k's, those terms all vanish. So you get an order epsilon term and an order epsilon cube term for the next order of approximation. Same story happens now. This manifold to the third order looks something like this. And this gives you the dynamics inside the manifold. Still, because you have gradients here, the minimizer is a fixed point of this system. And you can prove that it's asymptotically stable. The form of the Lyapunov function is a little bit more complicated because you have to add a term like this. But if you add that, actually serves as a Lyapunov function for this system, and you can prove that fixed point is asymptotically stable. One other comment about this third order approximation is that if you rearrange the terms a little bit, you can write it as x dot equal to this p inverse times gradient, where p inverse is given by this function, which is identity plus a term that involves the Hessian of f. And this is basically a preconditioned gradient descent. So the first order of approximation, the flow on the slow manifold is gradient descent. To the higher order of approximation, it becomes a preconditioned gradient descent. You can do this game for higher order approximations. It just gets more and more complicated to prove things. But first of all, notice that there is a limit to how far you can go into the approximation. Your function has to be r plus 1 continuously differentiable in order for you to go to r order of approximation. If it's C infinity, you formally can go to any order of approximation. But no matter what, at what order you truncate, you can also still show that the minimizer is a fixed point. In fact, all these functions, g2k plus 1s, vanish for x star, x equal x star. And also, you can construct a Lyapunov function that shows that they are asymptotically stable. The proof of that is kind of non-trivial, but if you look at the appendix in my paper, you can show that all these inner products are actually positive. This vanishes at x star, and derivatives of E along the trajectories are negative, and then it goes to the usual asymptotic stability results. Before I show you some examples on how this works in practice, here is the slide that I mentioned. I will say something about strong convexity. So it is a famous thing, well-known thing, that for Poyak iterations to converge, for you to guarantee that they will converge, you have to make this strong convexity assumption, meaning that you have to assume that f is strongly convex. And there are counterexamples that if you don't, you just require convexity, the iterations don't converge. But this is not true for Poyak's continuous system. You only require convexity, and then you can prove that actually the second order system, all the trajectories converge to the minimizer. And the lesson here being that discretization is tricky. When you go from the continuous system, as we already kind of saw in the schematic, you go from the continuous to the discrete system, things can look very, very different. Good point to emphasize that whatever I say today is about the continuous system. The hope is that similar results will hold in the discrete systems, but as already this slide shows, it's not immediate that you can just discretize any way you want and you get the same result. So let me show you a few examples. Let me see. All right. So what I will do is that I will consider three functions. I've taken them to just be two-dimensional and rather simple so that we can visualize all the dynamics rather straightforwardly. So these are the three functions which are listed here, example 1, 2, 3. They are all convex. These two are the parameters that correspond, these two columns are the parameters that correspond to the Poyak's method. One thing I want to emphasize, eta is not very important what it is. I just take it to be 1. But let a mu to vary between 2 and 8. The point being that at least on one of the examples, mu is relatively small. And trying to make the point that mu does not necessarily have to be very large for the existence of the slow manifold to be valid. When later on I'll talk about Nesterov methods, I'll show you examples on the same functions, but the only parameter that exists there is rho. As I said earlier, rho is usually 3 for you to get the Nesterov iterations when you discretize. But also in example 2, I put it equal to 3/2 to just again show that rho does not have to be very large for the slow manifolds to exist. So here are some of the visualizations of the state space of the system for Poyak's method. So I have a few elements here. The surfaces you see are not level sets of the function f anymore. These are the invariant manifolds themselves in the higher dimensional phase space. So the phase space for the system is 4-dimensional. I'm just projecting from 4D to 3D. So I'm only showing you the x1, 2 coordinate and one of the velocities, v1. For the first function, if you look at the shape of the function is quadratic in both terms. And because of that, the slow manifold you can show that is linear to any order of approximation. So you get basically a linear plane. Another element in these figures is the red curve, which is a trajectory of the full differential equation starting off the slow manifold in all three cases. And what I'm trying to communicate here is the fact that actually the trajectory converges very quickly towards the slow manifold. And then when it gets to the slow manifold, it follows the dynamics inside the slow manifold. The red curves are the trajectories of, again, the full system that started within the slow manifold. So they start from the slow manifold. They always stay on the slow manifold. And have their own dynamics. Trajectories of the full system can start off the slow manifold, but they converge very quickly towards it and then follow one of the trajectories on this slow manifold. And the origin here is the minimizer x star, and all these trajectories obviously converge to that. Same story is true for the second and third examples. This is the example, I think it was the second function where mu was equal to. And the point being that, again, you have still convergence towards the slow manifold, but because as mu is smaller, as it gets smaller, it allows for more oscillations as you converge to the slow manifold. If you pick a large mu, it converges very quickly towards the slow manifold without any oscillations and then follows one of the trajectories. But here you see that larger mu allows for larger oscillations. One more thing that I would like to point out is to quantify the convergence actually to the slow manifold a little bit more. So what I'm doing here, I'm writing the p order approximation of the slow manifold, and I'm denoting it with m epsilon p. So the slow manifold will be somewhere. It exists as an object, and this is just an approximation to that object, to the pth order of the expansions that I mentioned earlier. Now, what I do is that I take a trajectory like this one and compute its distance from the slow manifold to see how quickly it converges to the slow manifold. So now this is the distance to this approximated slow manifold. If you focus on the very few first iterations or the small time domain of the convergence, you see that initially the two trajectories, one corresponds to the distance from the slow manifold with one term in the series, and the other one corresponds to 3 terms in the series. Originally, they're converging with the same speed towards the slow manifold. But as you get very close to this actual slow manifold, because the black one is order only 1 approximation, the error does not decrease further to the actual, to further decrease further. But the better order of approximation, which is p equal 3, you go actually almost 1 order of magnitude in distance closer to the actual slow manifold. So basically, it's showing that the third order approximation is much closer to the true slow manifold than the first order approximation was. You can do the same thing for other examples. Similar results hold. One thing that would be, so this is like theoretically nice because it kind of gives you a geometric picture of how the accelerated gradient methods work. But from a practical point of view, it also gives you something. So if you look at the equations for Poyak's method or the corresponding discrete iterations, you'll see that obviously these are second order, so you need 2 pieces of information to supply in order to integrate these forward in time. You need an initial position x0 and some initial velocity v0. And if you look at the iterations, a similar thing is valid because at each iteration you need xk and xk minus 1. You need to give it 2 points x0 and x1 in order to initialize the iterations, right? Now, a nice thing about knowing where the slow manifold is the following, that you know that the initial phase of the evolution of the continuous system is just converging towards this slow manifold. It's not doing much in terms of converging to the minimizer itself. It's just you initialize it, it goes to the slow manifold, then converges to the minimizer. So the question is whether we can skip this part and then save ourselves a lot of iterations at the beginning, initial iterations. And it turns out that you can do that, and the trick is to take v0, the initial velocity, or when you go to the discrete iteration, takes x0 and x1 in a particular form. such that the velocity for the continuous case puts you very close to the slow manifold itself, so that you're not way off. If you take a first order approximation only in order to initialize your trajectory for optimization, then you only need one gradient evaluation to determine what the suitable V0 will be. But if you go to higher orders of approximation of the slow manifold, then you need the Hessian and higher order derivatives. That is probably not recommended. I would not recommend it. It takes a lot of time to compute those derivatives. But this is basically, supposedly you have a routine that already computes these because you're using a gradient method for your optimization. So you can just do one evaluation and get a good initial condition for V0. Let's see how in practice it really helps you in saving iterations in convergence to the minimizer. So what I'm showing here is the Poyax iterations for the function 1 from the examples that I showed, for which the slow manifold is basically linear. What I'm doing now, I'm doing two experiments. One, in both experiments, I start from the same x0. It's the same for both experiments. In the first experiment, I'm just using a trivial initial velocity. I assume that I don't know a better way to do it, so I just put 0. In the second part, which corresponds to the red curve, I use the first order approximation of the slow manifold to define the initial velocity. And then when you look at the convergence to, let's say you give it a threshold for convergence of 10 to the minus 6, it converges within a few hundred fewer iterations than the blue curve. So a judicious choice of the initial velocity saves you a few hundred iterations. What is important is that asymptotically, towards the end of the iterations, they're converging with no difference. I mean, there is a difference between them, but the gap is not increasing or decreasing. What is really helping you is at the first few iterations that the red curve really comes below the blue one, and then after a while they follow the same rate of convergence. The reason is that this judicious choice of the initial velocity saves you these few iterations at the beginning, and as a result, you're a few hundred iterations ahead of the other method. So a practical application of this method would be this. Let me say a few things about, I think I have, OK, good time. A few things about the Nesterov's method. So as I mentioned, it's a little bit more complicated. You have a singularity at t equals 0. As I said, this is integrable, so it really doesn't bother you that much. But the problem is that the geometric singular perturbation theory, at least in the original versions of it developed by Fénichet, was not set up to handle non-autonomous systems, but there are extensions of it for non-autonomous systems that were developed later on. So the trick here is really to look at the system in the extended phase space where you write these as system of first order differential equations, but you also consider t as a dependent variable. You assume that it depends on some pseudo time theta. Everything depends on that pseudo time theta. And basically, the rest is simple. You just write x dot equal v and write the equation for v. Theta dot is 1, so theta dot is really equal to theta. T dot is equal to theta, so it's just relabeling of time. But you do the same trick as before now. You divide by rho, and you get some small parameter epsilon, let's say. And then you rescale time and write these derivatives in the rescale time tau. So what happens essentially for epsilon equals 0 when you do all that is that still you have a critical slow manifold, or a critical manifold, where every point in it, a few things are important about it. Every point in it is a fixed point of the system for epsilon equals 0. It's a graph over t and x. And in the v direction, if you start off the manifold, you converge exponentially fast to this fixed point on the critical manifold. Now, when you increase epsilon, the question is whether this critical manifold deforms into a graph over the variable x and t, and whether you can write down the expressions for this manifold. And then the thing that is a little bit more difficult is that now t is running this way. So your trajectories start to move in time. your minimizer as a point in x and t is moving, but as a point in x is always really fixed. So if you take this fiber and project it back, it always goes to x star. And again, the same picture holds that any trajectory outside the slow manifold converges to this slow manifold m epsilon. Here is the formal statement of the theorem. Again, there is this condition that rho must be larger than some rho naught. But again, with examples, I hope to convince you that this rho naught does not necessarily need to be very large. So this slow manifold exists. And the trajectories converge exponentially fast to the slow manifold. And again, we have an expression in terms of like Taylor series expansion in epsilon or power series expansion in epsilon for this slow manifold. And now this even order terms do not vanish. However, we still have this sort of equations for determining g. g1 and g2 are given in terms of t and the gradient of f. And for higher order terms, g3 up, you have these recursive equations. Note that now g is a function of time and space x. So because the slow manifold in the non-autonomous case is a graph over time and space. One important thing to mention here is the fact that, again, if you look at the first order approximation or even second order approximation, but let's focus on the first order approximation where we only retain g1, we get epsilon g1. And that would be just a gradient flow again. Now, it's not very obvious because it has this explicit time in it, but if you're a little innovative and you scale time to define a t hat to be epsilon t squared over 2, it's a nonlinear reparameterization of your trajectories, basically, you get exactly the gradient flow back. So again, in the first order of approximation, the Nesterov flow is also the gradient flow. And you can do that for higher orders of approximation. The analysis becomes a little bit more complicated than the Poljac's method, so I won't go into that part of it. Examples, again, the three functions that I discussed for the Poljac's method, you can do the same analysis or the same experiments with those functions. In example 1 and 3, I put rho to be the standard value, that is 3. In example 2, I put 3 over half, just to show that even for smaller values of rho, it still holds. Now, it's kind of hard to visualize the manifolds when they're time dependent. So what I do is just I look at the sample trajectories of the system. Again, they start from, you see two trajectories. One, the black ones are from the full system, and the red is the reduced order system, which is basically gradient flow with a different time parameterization. So what you see is that the full system has some oscillations, but they all die out asymptotically, and you converge to the trajectory of the gradient flow. This is a maybe better the visualization, which is in time, x1 and x2, so I'm ignoring the velocity coordinates. You see, again, you have a lot of oscillations at the beginning, but eventually the oscillations die, and you converge to the trajectory of the gradient flow. Point being that the gradient flow is a first-order approximation of the Nesterov method as well. Well, just to conclude, a few things. The axillary gradient descent has a multiscale structure that you can use geometric singular perturbation theory to actually discern what that structure is. Important thing is that if you start off, it has an invariant slow manifold, and if you start off that, then your trajectories have two stages. First stage is kind of not very helpful because you're not doing a lot of work converging to the minimizer. You're doing a lot of work converging to the slow manifold. And then once you converge to the slow manifold, then you can follow a trajectory on the slow manifold that takes you to the minimizer. So there are two stages to it: converges to the slow manifold and then converges to the minimizer. I also give you recursive formulas for the slow manifold. To the first order, it's really just gradient descent, but it's the higher order terms that distinguish the Nesterov's method or Poljac's methods from the gradient flow. Those are the important terms. The second order Poljak method becomes a preconditioned gradient descent, which people have studied, but the connection hasn't been made that it's a second order approximation of a slow manifold. Also, you can use the fact that you know an approximation to the slow manifold in order to choose your initial conditions for the optimization in a judicious way, that saves you at least a good number of iterations and saves you. If your problem is really high dimensional, like 100 iterations is very important, right? If it takes you an hour to compute the gradient, then 100 iterations times an hour gives you 100 hours. So that comes in really high dimensional optimization that a lot of you already do, like as we saw in Petro's talk. With that, I'll stop. I'll just bring your attention to the manuscript that is available. All the details is in there. If you're interested in the details, if you have questions, you can reach me through this. If you're a student who is interested in doing a postdoc on these topics, send me an email. I'm looking for a postdoc who would be interested. So with that, I'll just stop. Thank you.